pre-calculator students, here we are with the binomial probability theorem, and we're going to use the binomial expansion to actually approximate some events, some probabilities. Now consider experiment where die is rolled 3 times. On each roll, the probability of getting a 6, we'll call it S, is 1/6. And not getting a 6, or non-6, N, we'll call 1 minus P, 1 minus a 6th, 5/6. So, to fill out the tree with probabilities, this is 6th and this is 5/6. And now these are conditional probabilities, but actually they're independent events, so it just always stays at 1/6 and 5/6. 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 And now a table of what can happen. Well, we could get 3 6s. And so that would be probability of 6, then a 6, then a 6, or 6, then 1/6 times 1/6 times 1/6, or 1/2/16 for the probability. 2 6s would be 2 6s and then a non-6, or it could be a 6, a non-6, and then a 6, or it could be a non-6, a 6, and then a 6. And those are different routes. But basically it's going to be a 6 times a 6 times 5/6 plus a 6 times 5/6 times a 6 plus a 5/6 times a 6 times a 6. So we get 15 out of 216. Wow, these are low probabilities, but that's what you expect. When you roll, you don't expect to get that many 6s. Now let's look at the chance of getting 1 6. So that could be a 6 and then 2 non-6s, a non-6, a 6, and then a non-6, a non-6, a non-6, and then a 6. So that's a 6 times 5/6 times 5/6. I think you see a pattern here. 5/6 times a 6th times 5/6. And then 5/6 times 5/6 times a 6th. So 25, 25, and 25 is 75, 216. Now we're getting somewhere. And lastly, no 6s means non-6 times non-6 times 9/6, coming down this end of the tree. So that's 5/6 times 5/6 times 5/6, and we get 125 2/16. So they're sure enough, these all add up to 216 over 216. And we could have also done this way by taking p plus 1 minus p to the third, which is actually just 1 to the third, or 1. So this expansion should all add up to 1, because either our roll is going to be a 6 or it's going to be a non-6. So we could think of it as p to the third plus 3p squared times 1 minus p squared plus 3 times p times 1 minus p squared. I'm sorry, I got the wrong power there on that first p. Let's get that micro changed. There we go. Plus 1 minus p to the third. And so there you go, the binomial expansion. And see how that corresponds to what we did up here? And this coefficient from Pascal's triangle, it's counting all the ways you could get the ordering. And this is counting all the ways you can do the multiplying of the 2 6s and then 1 non-6. So if we rolled 4 dice instead of 3, now we'd have to use the 4th row of Pascal's triangle. P to the 4th plus 4p cubed 1 minus p plus 6p squared 1 minus p squared plus 4p 1 minus p cubed plus 1 minus p to the 4th. And those would all up to 1 as well. So the binomial probability theorem, suppose an experiment consists of a sequence of n repeated independent trials. Very key idea here, independent. And they got to repeat. It's got to be the same trials. And it's got to be a fixed number of trials. Each trial having 2 possible outcomes, A or not A. And if on each trial the probability of A is P, the probability of not A is 1 minus P, then the binomial expansion of this will tell you those probabilities. NCN P to the N plus ... Somewhere in the middle we're going to have NCK P to the N minus K 1 minus P to the K. The powers in 1 minus P will build up. gives the following probabilities for the occurrences of A's. So n A's, to get all A's would just be NCN, which is 1, P to the CN, P to the N, or just plain P to the N. And that makes sense. To get n raised in a row, you're going to take that probability and multiply itself n times. 0 A's would be the other n, NC0, 1 minus P to the N. And NC0 is 1 as well, so that's just 1 minus P to the N. The tricky one is this KA's, would be NCK, P to the K, 1 minus P to the N minus K, and there you go, or n factorial over n minus k factorial, k factorial. I'm going to repeat this in the sigma notation down here. P to the k, 1 minus p to the n minus k. So in sigma notation, k equals 0 up to n. NCK, that'll give us our coefficient from Pascal's triangle, or precious mirrors, times p raised to the n. And then the 1 minus p's build up. And so that's the n, I'm saying p to the n minus k, and this is p to the k. Need my little eraser again. There we go. So k, the 1 minus p's, the failures start off at 0 and build up to n, and you start off with n successes. Example 1, a coin is tossed 10 times. What is the probability of exactly 4 heads? So we're expanding out heads plus tails to the 10th. And we could do the whole expansion. This is 11 terms. Just need the term that has heads to the 4th. Heads to the 4th, that means you're going to have basically tails to the 6th. And then it'll be 10 factorial over 4 factorial, 6 factorial. 10 times 9 times 8 times 7. 6 factorial cancel out with that over 4 times 3 times 2 times 1. There the 4 times 2 get 3, 20, 210. And h is a half. That's the probability of the head is a half. And the probability of the tail is a half as well. And so we get 210 over 1,024. That's 2 to the 10th. You can keep it like that. If you want to reduce it, you can get 105 over 512. That's fine too. Or let's see if it works out. And that works out to be about the 0.205 we got down there, a little more than a fifth. Now example 2, in a survey of 1,000 students in a school, 950 indicated that they were right-handed. Find the probability that at least one of the 4 randomly chosen students from the school is left-handed. Why is this not technically not a binomial experiment? Well, the probability that the first is right-handed is going to be 950 out of 1,000, right? And so that's 0.95, 95% chance. The probability that the second is right-handed, given that the first is, we're going to end up with, if the first was right-handed, now we have 999, and this is 949. 949 out of 999. Let's see what that works out to be. And it works out to be 0.9499499. So basically we're repeating this, 0.949, which is a little less than 0.95. So the probability's changed. Now this statement itself doesn't quite do it. And you're actually going to see that the probability that the second is right-handed actually ends up being 0.95 as well. But they're dependent events because these two, the probability that the second is right-handed given that the first is right-handed, and the probability that the second is right-handed, they're not the same, therefore we have dependent events. So technically you can't use the binomial probability theorem, but the probability changes so little over the course of picking out 4 students that we're going to proceed and use it as an estimate. There's something called the hypergeometric that can be used for this, and that's the study of the next section. So find the probability that at least one of the 4 randomly chosen students from the school is left-handed. So the probability of at least one left-handed kid in the 4 that you pick. And remember, we're picking 4 randomly chosen students. So it's right-handed plus left-handed to the 4th power. And we're essentially doing this expansion: right to the 4th plus 4 right to the 3rd left plus 6 right to the 2nd left to the 2nd plus 4 right left to the 3rd plus left to the 4th. And you want at least one left. Here you want all these. And so I think you can see that it's easier to do 1 minus the probability of not at least one left-handed student. So it's 1 minus the probability of all right-handed. And we go 1 minus then the probability of basically r to the 4th. So 0.95 to the 4th. So you put that in the calculator and you should get that 0.185. Let me just check that. Yes, and that's the case. So now let's see how you do this on the T89. There's 2 approaches. You can use binomial PDF and binomial CDF. PDF is for finding a specific term in the expansion, like if I had asked what's the chance of one left-handed person, and you could put in the number of successes right there. If you leave that out, it'll actually give you the whole list of all the probabilities. Binomial CDF I find the most useful, especially in this one, is finding a sum of terms cumulative in the expansion. If you leave out the 3rd and 4th part, you'll get a sequence of partial sums of the expansion, so it'll give you something like what you got with binomial PDF without this one. So on this last example, we could do binomial CDF. Our n is 4 kids. The probability of, we want the chance of a left-handed kid, so I'm going to use 0.05. And we want at least 1, so we want to go from 1 up to 4 left-handed kids. And let's see how this works. Binomial CDF, 0.05, 1 to 4. And it works. You get 0.185 again. Now remember, this is in Flash apps. After you go to the catalog, then you have to go to Flash apps. And if you don't have those Flash apps, some of these come with the stats applications, and I can get those onto your calculator. So we talked about that for the current example. Now, example 3. Of the computer operators who work for a large temp agency, 60% have a car. If 5 of the computer operators are randomly chosen to work on a job that requires a car transportation, what's the probability that at least 4 have cars? So the probability of at least 4 have cars. You might want to identify some of the players in this. N, in this case, is the number of people you're pulling on this trial, and that's 5. R equals the number of successes. Also in the calculator, it's viewed as X. And so we want the probability of at least 4 cars, so R equals 4 or 5. The probability of it having a car is 60%, so that's 0.6. And so 1 minus P is 0.4, sometimes also called Q. So when we think of this expansion of car plus no car, and raise it to the 5th, we don't want the whole expansion, we just want the terms that have car to the 4th, so not a car to the 1st, and car to the 5th. And it's toward the end of the expansion where the coefficients would be 1 there and 5 from Pascal's triangle. So I left a lot out, but I only really wanted to know these 2. So it's 5 times the chance of a car is 60%, so 0.6 to the 4th, not a car is 0.4, plus 0.6 to the 5th. And let's calculate those out. Also, you have your binomial CDF command, CDF, cumulative, and you're going to put in n, which is 5. The chance of success, that's a car, that's 0.6. And the lower amount is you want to go anywhere from 4 to 5 cars. Let's make sure these both work. Yep, for the top one I get 0.33696. That checks. And for the binomial CDF, let's try that as well. And that checks out as well. Okay. Next. No more next. That's it. Flange out.